Hey everyone, so today I'm going to be teaching the backtracking coding pattern. And yeah, backtracking is just an essential algorithm or coding pattern that you need to have in your tool set. It helps you understand recursion and it builds up towards top down dynamic programming. So yeah, you really need to know backtracking. You'll see this come up a lot in graph questions and you'll see it all over the place. It's essentially a brute force. It's essentially how you do brute force. So when you see a question say something like generate all, or you actually need to search all paths to find a given solution, and you can't just get there more optimally using something like a greedy algorithm, then you're gonna have to pull out the backtracking algorithm. And what exactly is backtracking? Like I mentioned, it's brute force, but conceptually, you can imagine it as a tree traversal on a decision tree. We're essentially taking paths, taking decisions towards a solution. And if we ever get to a case where we run out of decisions to make, or the decisions that we've made are wrong, then we backtrack and try a different path. So, what do I mean by that? Say that we're making decisions. Pretend we have three decisions. We're making one decision, or one decision, two decisions. Once we make our third decision, we run out of decisions. Then we hit our base case. Then we can recurse backwards, right? And then maybe we go down this third decision, and that works as well. And then we backtrack and then we have this backtrack step essentially when we're making decisions. At some point, if we run out of decisions, we will have to backtrack and then try a different path. This is the case where we need to generate all. But pretend that we also have the case where pretend we make a decision and we automatically know it's wrong. Then we need to backtrack as well. So how would that look? Pretend we make this decision one, decision two, and we know that the decision is wrong right away. Then we need to backtrack and then try a different decision, and maybe that decision leads to the right answer. So you most of these backtracking questions, you can generate all, or yeah, there's ones where you have to generate all, and then there's ones where you need to search all the different paths for solution. I'm going to show both of those ways. I'm going to show questions where you have to do both, or I'll have one question that does this one and another question that does this one. So you see the two different variations of backtracking algorithm. But in either case, both of them have pretty much the same boilerplate where we have some base case. It's just a recursive algorithm where we have some base case where we want to end the recursion. In each recursive step, we add one of our choices to the solution, and then we recurse, so we can continue making more decisions. That's why it builds out sort of a tree. But in any case, we hit a base case. When we return, we need to actually undo or revert the choice that we made here. So pretend we made this choice, then we made this choice. We need to revert this choice when we backtrack. And that's the subtle difference between a backtracking algorithm and a DFS. It's this backtrack step where we have to revert the choice from our path or from the solution before we explore a different path in our decision tree. I hope that makes sense. I think it'll make a lot more sense when I work through the examples. So yeah. So this is the first question that I want to walk through, and this question is one of the ones where we have to generate all. It's this case. So it's pretty much saying we're given an integer array of numbers, and we have to return all of the possible subsets, the power set of this. So what are the possible subsets? The possible subsets is you take none of the elements, you take just one, you take just two, you take just three. It's pretty much all the different ways that you can pick from numbers here and create an array, and order doesn't matter. So 2 to 3 here, is equal to 3 and 2. It's more just the choices that we make and not the actual ordering. That's a permutation. But yeah, the goal is to return all the possible subsets of nums, right? And what gives it away that it's a backtracking algorithm right away is it says return all possible subsets. So we have to generate all. So yeah, also the solution must not contain duplicate subsets. Return the solution in any order. So how are we going to do this? I mentioned already that we have a template for backtracking. So I'll just write that right here. The way I like to do this is I like to create a backtrack function. And I'll just actually store that. Store that right here. So yeah, we're given what we're gonna do is we need to return some sort of output here. So the way I do that is I like to pass it down a result, and I like to store decisions path. Did I spell this right? Yep. So we have decisions, path, and a result, right? What I mentioned before is I also like to pass in an index. The index, pretend our decisions are 1, 2, 3 here. Our decisions are pretty much, or our index tells us what decision we need to make. So we either decide to include this into the result or we don't. And I'll show exactly how that works. And maybe I'll draw out the recursion tree so it makes it, or the decision tree, so it makes it a lot easier for you to understand. But let's say, what's our base case here? Our base case is if the index is greater than or equal to the length of the decisions. That means we've already made all the decisions that we want. We want to return that. And then what we want to do, yeah, that's our base case. And actually what we want to do in this question is once we hit our base case, we're going to want to add the current path of decisions to our result. Result.append for lm in path. We want to create a copy of our path. And then we have to add choice to solution. So pretend we're at the index. Well, we have two choices. Pretend we're at the number 1, right? We have two choices. We either want to include 1 in our path or we don't include 1 in our path. So that's our choices. Include 1 or include the index or don't include it. If we include the index, what are we going to do? We're going to say path.append decision at index, and then we're going to recurse self.backtrack. Since we already made the decision, we do +1. Our decisions go down here, path and result. We just pass down the reference to the path and result. So we add the choice of solution, we recurse, and then what we eventually need to do is backtrack. So we say path.pop. That removes, so we try going down that path, but then we need to pop it out. We need to do the backtrack step. So this is this. Right. So this is if we choose to go with decision. We also have the case where we don't pretend we're at 1, right? Pretend our choice is either choose 1 or don't choose 1. So we have to choose that element, choose element, or don't choose. If we don't choose, then we just increment the index and we basically just like skip one and don't include that at all. Right, and then we return here, and then I'll actually just draw out the complete decision tree here, so it's easier for you to see. But what we'll do is we'll have our result here. Maybe we could just, yeah, we have our result here, and then what we'll do is call backtrack. Then we'll eventually return our result, self.backtrack. We're gonna start at index 0 because that's the first decision we have to make. We're gonna be given noms. These are the decisions that we can choose from. We're giving a path, which is empty, and then result. I think that should just work out the box. Beats 100% runtime. That's the backtracking algorithm. That's how I wrote it, and I'll draw out the decision tree for you now. Let's see if I can. It might be good to just take a picture of this. Or let me take a picture here. So pretend in this question we're given nums 1. Pretend in this question we're given nums 1. We start with the case. These are our decisions right here. Decisions. And we have the index points to what element or what decision we need to make. We need to make the decision to choose this or don't choose it. As mentioned, we have an empty path. Pretend. So we start with empty path and we have some result. Result is where we're gonna store the final, all the subsets. But pretend we go into this case and then we decide to actually choose this element. Then we add 1 here. That's what this code is doing. It's adding the decision to the path, and then we recurse here. So now we're at 2. Then pretty much when we call this function, it didn't reach the base case because we still have decisions to make. The index is actually still less than the length of the decisions. So again, we choose option 2. So you'll see that we append to the path. So we can choose option 2 here. And then we recurse again. And then we get to option 3. And then it still hasn't hit the base case. We still have more decisions to make. So let's say we want to include 3 in the result. So we get 1, 2, 3. Right? And now finally we move this. And finally now we're at the base case. So we add this to the result. This is a subset that we want to add to the result. That's what this logic right here is doing. It's adding this to the final result, like a global variable where we're going to maintain all the subsets we've seen, which will basically be the leaf of all of these decision trees. But now when we go back to 1, 2, we want to get our path to look like this so we could explore a different path. We don't want to have the 3 in there because it's going to affect because we want to get back to this state. So that's what this important part of backtracking step is, where we pop from the path. So we pretty much pop this element, and then when we recurse, we get back to this state, and then we can try out a different option here. Pretend we decide not to choose 3 here. We choose not to choose 3. We get back to this result. Like we're here, we choose not to choose 3. We get back to this result, and then we reach the end. And since we're out decision, this is also a leaf, and this is also a base case. So we add that to the result as well. So you could see that's kind of how this logic works. And then when we you can see since we were at this path, we didn't add anything to the path, so we don't even pop anything after when we return. But essentially when we hit 1 2 here, we need to backtrack as well and move this 2 and explore another path. Hope that makes sense. That's how I look at the recursion tree. You're pretty much making decisions, and when you backtrack, you have to remove that decision you made off of the path in order to get it back into the state it was before. So if I backtrack again, I need to pop the 2 out. So yeah, that's how you solve the subsets problem. I hope that made sense. Try to explain as much as possible. Just leave comments if you don't understand it, and we're going to move on to the next example. So this next question is called word search, and we're given it's pretty much an example of this one where we need to search all paths for a solution. Where are we? So what's the question? We're pretty much given a grid of characters and a word, and we need to just return true if the word exists here or not. So the word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring, and the same cell may not be used more than once. So when we search A, B, C, C, E, D, we need to basically just look for that word in this grid. And we can only use each character once, and we can't skip steps. That's essentially what it's saying. So it's just like a simple word puzzle where you just need to find a word inside of a grid or inside of an array or matrix. I'm not sure what regular people will call it. Maybe it more aligns with a crossword. But yeah, we just need to search for the word in here. And you might be thinking that we can use a simple DFS here, but the backtracking step is important, and I'll show a case where that happens. Pretend we're searching for AAAADA. So the final path is actually this. Pretend we're performing a simple DFS. We start A, or we go this path. And then here we have a decision. We either have to go A here, or we go down this path. If we decide to go down this path, it's not really fruitful because we can't go diagonal. So we can't keep extending. We can't keep searching this way in order to find the word we're looking for. We actually have to backtrack and try this path to get the result. If we did a simple DFS where we added this element to the scene arrays to avoid cycles, and then we eventually went down this path, when we get to D, we won't ever visit this node again because we added to some scene array. So the backtracking step is important because it's still important to add things to the scene array, because as we mentioned here, we don't want the same letter used more than once. But we want to, if we lead to a path that's not fruitful, we want to remove that from the scene array, or we want to remove that from the path in general, because we want to eventually we might want to visit again because it might actually be part of the solution, like in this case. Hopefully that makes sense. I'm gonna go implement this this word search and then show you how the code works. So like I mentioned, we create a backtrack solution or a backtrack function, and all of them pretty much have this same exact template. It's just literally copy and paste, where we have our base case here. So the way I like to do it is, yeah, we have our base case, we add a choice to the solution, then we recurse, and yeah, we eventually need to undo. So what we need to do is we need to pretty much, since we're looking for a word, how we solve this problem is we need to try doing a backtracking algorithm on every single cell in this grid, right? And what the backtracking algorithm is first gonna do is it's if pretty much what we're gonna do is, let me just take a picture here. Let's do this in a scally draw because it's gonna make more sense. Or let's work through this example. Pretend, or let me reverse a bit. Pretend this is a bigger array. We have X, Y, Z. And we're searching for AAD. What we're gonna do is, well, we only want to start the backtracking algorithm when we hit, when the element we're looking at matches the first element here. So since X doesn't match, then we don't really need to try it. Since Y doesn't match, we don't really need to do a backtracking algorithm. If Z doesn't match, then we don't need to do a backtracking algorithm. But then when we reach A, we know that we need to do a backtracking algorithm because we know that this might actually we might be able to find the word there if we start from here. So that's essentially when we start the backtracking algorithm. So for this case, well, what we're going to do is return false if we don't find anything. But what we're going to do is we're going to loop through every element, and we're going to look for a start point for our backtracking algorithm, So for row in range length of board, for column in range length of board 0. This is how we loop through the rows and columns. If the board at row and column, what are the constraints here? So if the element at the row and column is actually equal to the first element here, we're gonna perform our backtracking algorithm. So we'll say result equals backtrack. So what we're gonna do with our backtracking algorithm, like I mentioned before, we're gonna have our decisions. We have our index, and our decisions is going to be the word. We pretty much have one decision. We need to choose that element if the index matches. So basically, our decisions is like A, B, C, D, E. And then our index points to the character that we need to find next. So first we need to find A, but when we recurse, we need to find B next. So we have our decisions, our index, we have our path, and we have our result. What's our base case? If the index is equal to the length of decisions, that means we've already found all the characters in the word. So let's just say word right here, because we're looking for the different characters in the word, and we only recurse if we find a matching character. So if the index is equal to the length of the word, return true. That's our base case. Otherwise, we return false. So what do we do? What are the different, pretend? What we'll do is we'll do a backtrack here, self.backtrack. And we're going to be given the word. We're going to be given our index, which, since we already know the first character matches, then we only need to look at the next characters after. So we'll do 1, and then we'll pass in our, do we need to care about the path here? Yeah, we need to care about the path because these are the elements that we visited. Because so to hit this constraint of the same letter cell may not be stored more than once, but we could actually just maintain a set here because we just need to maintain what cells we've already visited. and we don't really need to return a result because we're not generating all. So it's a slight difference, but it's very similar code here. But yeah, we'll say if result is true, return true. That means that we're able to see if we can find the word. Otherwise, we'll start at a different index. So we have to add the choice to solution. Set equals, we'll say, we'll create a set with the row and column. So what we're going to do is, since this is, we need to look for the neighbors in order to figure out, we need to explore the different paths. And what are the different paths? Well, it's the adjacent, horizontal, and vertical neighbors. So yeah, here we're also going to be given we're actually going to have to pass down the board, the row, and the column as well. You can see I'm slightly adjusting this. The board, the word, row, the board, the word. Yeah, the board, the current row and column. But we need to look at the neighbors. So the way I like to do to look for the neighbors is row column here. You could see me thinking about the solution real time. I didn't even prepare the solution, but that at least it helps you think about how to solve it. So how do we find the neighbors? Well, we need to do the adjacent horizontal and vertical ones. So how I have to look above me. So I have to take the current row and -1. I have to look to the right, so call +1. I have to look bottom, +1 here, and I have to look to my left. So those are my neighbors, and I'm going to try looking at those neighbors to see if I can get to a result. So for neighbor row, neighbor column in neighbors here, what we're going to do is if we haven't already visited, if these aren't already in our path, if it's in our path, we continue. Because we can't add it to our path. We can't recurse on it. We can't make that decision if that was already part of our decision tree. If that element was already part of our decision tree. But what we're gonna do is we're gonna look for, we basically only want to recurse if it's a B here in this case, because we already know it's an A. So what do we do here? If the board, we need to do some bounds checks, right? If the neighbor row, because we're gonna look up, right, down, and left. If we look up, we might get we might get index out of bounds. So if the neighbor row is less than 0, or neighbor row is greater than equal to the length of the board, just continue because that's out of bounds. And then we have to do the same thing for columns. We have to do the same thing for columns here. So we're just making sure that it's in bounds. If the board at the neighbor row, neighbor column is actually equal to the next character we're looking for. So we'll say is equal to word at the index. Then we'll actually finally do our recursion again. So what we're going to do is we're going to take our board, and instead now we're going to recurse into our neighbor. Neighbor row, neighbor column. And then we'll say here we do index +1. And then we're going to pass down our path. But like I mentioned here, we're going to have to add choice. This is where we finally make a choice. We only make a choice when it's actually a valid choice, because pretend we're looking for B. We don't want to make we don't want to explore a path where the next element is C, because we have to look for the word in this specific order. So we finally make choice here. So how do we make a choice? Well, we do path dot add. We add the neighbor row and neighbor column to our result here because that's how we simulate making the choice. And then worst case right here, path dot add, and then if we actually explore that path and it works, then we return true here. Otherwise, that path didn't work, so we have to kind of remove here. This is the recursion step, and this is the backtrack undo step. I think with that logic, let's just try running and see if it works out the box. No bugs. Nice. Cool. Yeah, that's the backtracking algorithm. I explained why you need backtracking for this question. I showed how you modify the boilerplate and some of my decisions around the state. So let's just get into the common pitfalls. I think the main one is when people don't undo the state correctly. So you can see here I'm undoing the state. That's really important for backtracking algorithms. What else? Not handling the base case. So we need to figure out when to stop our recursion. So having a base case here is important. We also need to know what to do when we hit the base case. So for this case, we just return true. But for the generate all case, we need to add to some result. So yeah. So also there's also there's optimal ways to actually cut off branches early. You can make the algorithms a lot faster if you pre-sort. And yeah, there's also other questions where we need to be able to handle duplicates. And yeah, those are the common pitfalls to backtracking, I guess. I'm just trying to think of the last two, but yeah, definitely there's ways. These are more just optimization things. And I didn't really get into this video, but I think what I covered is most of the basics for this pattern and algorithm. And yeah, I'll see y'all in the next video.